acids and bases. Today we will be going over strong acids and bases, how to approach different acid-base problems, and my favorite, buffers and titrations.
For the basic stuff, like what an acid even is, refer back to Hudson's Unit 4 videos. If it doesn't make any sense, you have my permission to boo him in person.
Boo! Let's start with some reminders about concepts that are easy to forget. First, only one hydrogen ion is transferred at a time, even if it has more than one hydrogen ion.
Second, hydronium is H3O+, which you'll see as H+, while hydroxide is OH-. Don't be stupid like my old student Katelin, who would get those mixed up.
Third, pH and pOH are always related to each other through the water dissociation constant. Kw equals 1.0 times 10 to the negative 14th, which also equals the concentration of H3O plus times the concentration of OH minus. We see that 14, which is the exponential constant, equals pH plus pOH. But this is true only if the reaction is at 25 degrees Celsius. What happens when the temperature of the water increases? Does the pH and pOH change?
At least say something.
Yeah, it changes because when the temperature increases, it drives the reaction to the product side, producing more H+ and OH- ions. So when you have an increased concentration of both, that decreases the pH and the pOH, which changes the Kw constant.
Excellent, my lovely electron. For example, when water is at 40 degrees Celsius, the acid dissociation constant for water becomes 2.92 times 10 to the negative 14, which means the pH is now 6.767 and not 7.
Even though you guys are probably already watching this on double speed, let's move right along to strong acids and bases.
How's that work?
Strong acids and bases dissociate completely. Now, you need to memorize your strong acids and bases for the AP test.
Go ahead and try to recite them all right now. What are the strong acids?
H2O, NaCl, and HF. Good try, but none of those are correct. Even HF is not a strong acid. There are 6 strong acids: HCl, HBr, HI, HNO3, H2SO4, and HClO4. F, although in the same group as Cl, Br, and I, has a very high electronegativity and a terribly small radius, which makes it hard for it to donate a hydrogen ion. That's why it's considered weak and not strong.
If you don't know your strong bases, you should just go back to the basics. But since we're so nice, here they are. Literally just group 1 or group 2 metals combined with OH-. Mind the charge for group 2. It's CaOH2, not just CaOH.
But what makes these so strong?
If you look at the molecular structure of the strong acids, you'll see that all the oxygens, chlorine, bromine, and iodine are bonded to the central atom, and the hydrogen is off to the side. This draws all the electron density towards the center of the molecule and away from the hydrogen. Remember, strong acids love to get rid of their hydrogens, just how Katelin loves to get rid of Lennis. And so, when the electronegativity is drawn away from the hydrogen, the loosely attached hydrogens come off and the acid dissociates easily. Isn't there another explanation? You could also look at the resonance of the conjugate base. If the conjugate has a lot of resonance structures, that means it's stable, so the acid likes to be in that conjugate base form rather than the less stable, strong acid state.
Yep, that's right. And don't worry about explaining the strength of strong bases, because it's not on the test. Just know that they love to accept protons.
Alright, let's review some problems now. Any acid-base problem you see can be put into one of 4 categories: dissociation, half equivalence point, or unbalanced.
The first category, dissociation, is when an acid or a base is in water without any other compound. You already know what will happen when strong acids or bases are in water, right? They dissociate completely? Yes! So then you can take the molarity of the acid and go straight to the pH, or you can take the base and go to pOH, then the pH. Let's practice one.
Katelin wants to poison Lennis with a solution, naturally. She has 50 milliliters of water and 20 milliliters of 0.5 molar concentration HCl in her basement. When she mixes in the HCl with the water, what will the pH be of the final solution? Take a minute to try this one on your own.
2,000 years later.
Okay, I bet you didn't try it on your own and just kept playing the video, but we'll go through it anyways. I hope you identify that HCl is a strong acid, meaning it dissociates completely in water. There's only the conjugate left, and we don't have to worry about a K constant because it's not an equilibrium reaction. What is left dissociated in the water is H plus and Cl minus. We don't care about Cl minus because it's a weak conjugate base and it has minimal effect, but we do care about H plus.
20 milliliters times 0.5 equals 70 milliliters times X. And we know that this is the second molar concentration, which equals 0.14 molar concentration of HCl. Don't forget sig figs, which means this would end up becoming 0.1 molar concentration. Since we know that the initial concentration of HCl in the mixture is 0.1 molar concentration and HCl is completely dissociable, then the mixture would have a 0.1 molar concentration of H+. Plug this into your pH equation, negative log of 0.1, and then you should get 0.84 as your final answer for the pH.
Okay, easy one done. Now we have to cover weak acid or base dissociation. Let's look at an example. While attempting to pour some acid into Hudson's drink, Lennis spilled a cup of acid on the floor and it needs to be neutralized. She has a basic 100 milliliter solution of 0.8 CH3NH2. The Kb value is 4.4 times 10 to the negative 4. What is the pH of the solution? Try it right now.
One eternity later.
Okay, what'd you guys get?
0.09691. You just take the negative log of the concentration of the base. I can see where you're coming from, but this is different. That would only be the case if it were a strong acid. In the case of a dissociation of a weak acid or base, you can approach this problem using an ice table.
Okay, buttercups, make your table and fill in what you know. Since we're dealing with a weak base, we don't know how much is going to dissociate, but we do know that it's not going to be very much because it's not a strong base and because the Kb value is quite small. So we know our initial concentration, but we'll put in variables for the change and n values. So we know our initial concentration and we'll put in variables for the change and the n values. Since not a lot is going to dissociate, we can neglect the change done to our initial value. Now we're going to set the equation for the Kb value. Kb equals products over reactants, so 4.4 times 10 to the negative 4 equals x squared over 0.8. X equals 0.01876, which equals your OH minus concentration. We can take the negative log of that, which gives us a value of 1.72677, which is pOH. Exactly, not pH. And to get the pH of the solution, which the question is asking for, we have to do 14 minus 1.72677, which equals 12.3. Don't forget to do that extra step when you're going from pOH to pH when you're dealing with a base.
So that covers dissociation. Now, let's look at acid-base neutralizations. We'll start with equivalence point problems. We can approach the problem using a BCA and ice table. Here's a problem. Johnny and Hudson are lab partners once again. Sorry, Johnny. They're tasked to calculate the pH of HF at the equivalence point. They have 50 milliliters of 0.100 molar concentration of HF and 50 milliliters of 0.100 molar concentration of NaOH. The Ka of HF is 6.3 times 10 to the negative 4th. What is the pH of the mixture once the solutions are combined? Why don't you students try this?
The pH is 7.95.
Wow, you're awfully smart for your age. That is correct. Now, let's go step by step to explain to your struggling peers. The reaction equation is HF plus OH minus produces F minus in water. In order to find the concentration of F minus, we need to find the moles of each solution. Using dimensional analysis, we have 0.005 moles of HF and 0.005 moles of OH minus. Wow, this is really convenient because this means that all the HF and the OH minus will react because they are at a 1-to-1 ratio in the equation. This is what's called the equivalence point. Using a BCA table, we get 0.005 moles of F minus and some water. We're halfway to the answer now. Knowing F minus, a conjugate base, we can use a dissociation equation to find the pOH of the reaction. This is where we need an ice table since we're looking at dissociation now. We can calculate the molarity of F minus to get 0.5 molar concentration. Great! Let's plug this into our table. Utilizing what we learned in the last few problems, we can calculate the pOH. Remember, F minus is a base that reacts to create OH minus. This should tell us to use Kb and the concentration of OH minus to find the pOH, not acid. The problem gives us the Ka value of HF, 6.3 times 10 to the negative 14th. Using the equation Kw equals 1 times 10 to the negative 14th, which equals Ka times Kb, we can find Kb, which is 1.6 times 10 to the negative 11. Then, knowing that Kb equals x squared divided by 0.5, we can find x to be the concentration of OH minus, which equals 8.9 times 10 to the negative 7th. Now, remember, we know that pOH equals the negative log of the concentration, which means when plugging this in, we get 6.05. 14 minus 6.05 gets us the pH, which means that the solution is 7.95. This is so hard. Why aren't you giving us easier problems?
Alright, we'll stick to your level. Here's the easiest reaction problem in acid-base, half equivalence point. This is when exactly half of the moles of your starting acid or base reacts.
To do these, you use Henderson-Hasselbalch's equation. I promise you this approach is not a hassle. Here's your problem. Hudson and Jacob decide to mix some acid and base and wonder if it's safe to drink. They mix 50 mils of 0.2 molar concentration of HF with 20 mils of 0.25 molar concentration of NaOH. The Ka value of HF is 6.3 times 10 to the negative 4th. What is the pH of this solution once mixed? Try this problem on your own.
Whether or not you guys did it, let's take a look. First, set up a BCA table using millimoles. I hope you recognize that NaOH is strong and it dissociates into OH minus. From here, you can see that the amount of moles of HF is twice as much as the amount of OH minus. So we have a half equivalence problem on our hands. If you were to fill out the whole BCA table, you'd see that at the end of the reaction, the amount of HF is the same as the amount of F minus. When you plug it into Henderson-Hasselbalch's, B over A equals 1, and so the log of 1 is 0, and you just have pH equals pKa, and so you take the negative log of the Ka value, which gives you a pH of 3.2. Just remember, if you see a BCA table and see that it's half equivalence, just go straight to pH equals pKa. This concept will come up again later when we talk about titration curves.
Okay, now we just have our last problem type. Unbalanced reactions, meaning neither half equivalence nor equivalence point. For these, you're going to set up your BCA table and assess what stuff you're left with at the end to calculate the final pH. Let's look at our problem. Mrs. Han is doing a super cool experiment. She mixes 50 milliliters of 0.5 molar concentration of NaOH and 40 milliliters of 0.1 molar concentration of HNO2. What is the pH of the final experiment? I don't really want to solve it. Can we just go over it? Okay, let's BCA it out again. Multiplying the volume and the concentration, we have 25 millimoles of base and 4 millimoles of acid. When we subtract the change, we end up with 21 millimoles of OH minus, 0 millimoles of HNO2, and 4 millimoles of the conjugate base NO2 minus. However, because OH minus is a much stronger base than NO2 minus, the additional OH minus ions that are created from NO2 minus's dissociation are basically negligible, meaning that we can ignore it. That's why when we want to find the pH, we only care about the leftover OH minus that is remaining from the initial amount. So, when we have 21 millimoles, we can divide it by 90 milliliters to get 0.23 molar concentration of OH minus ions. That's why when we negative log it again, we get 0.63 as our pOH, which means our final pH is going to be 14 minus pOH, which gives us 13.37. That was a lot of content, but good job guys for pushing through it. We're going to shift our attention slightly now and look at buffers and titrations. Who remembers what a buffer is?
Ooh, me. It's a solution of a weak acid or base with its conjugate, and it resists changes in pH.
Excellent! And it's able to resist change because any acid or base added gets neutralized by one of the components of the buffer. For example, if you add an acid, it'll react with the base in the buffer.
So, how do you make a buffer?
You mix stuff until the pH stops changing.
Nope, there are two ways that you can make a buffer, and neither one is that. You can either mix a weak acid or base with its conjugate, or you can react a weak acid with a base so that you'll get around similar amounts of conjugate and acid. Same thing goes for base, but don't forget this. You cannot make a buffer with a strong acid or base, because it would all dissociate into conjugate. And to have a buffer, you need to have a balance of an acid and its conjugate.
Exactly! So when you see a multiple choice answer that says you can make a buffer using a strong acid or base, cross it off immediately. There's more to think about with buffers, like the buffer zone, but to introduce that topic, we'll have to go over titrations first.
Alright, we all know what a titration is. You have a burette with a solution of known molarity, your titrant, and you drip it into an unknown solution, your analyte, until your indicator tells you you've reached equilibrium by changing colors. Let's run through graph shapes. Here's the general shape of your acid titration, and here's your base titration.
Here are some key components of the graph that you need to identify. The equivalence point is where there is a sudden increase in pH for the acid and a sudden decrease in pH for the base, because at that point there is the same amount of acid and base, and one drop of the titrant over the equivalence point makes the whole solution tip to the opposite acidity level. The equivalence point might not exactly be 7 because there is still a product conjugate that affects the pH, the dissociation.
You'll find the half equivalence point by looking at the volume of titrant required to reach the equivalence point and halving it. Since it's half equivalence, we know that pH equals pKa, so if you're ever supposed to find the pKa of an acid based on its titration curve, look for the half equivalence point. This is also the buffer zone because there are relatively equal amounts of acid and conjugate base, or base and its conjugate acid.
And that just about wraps up our review on acids and bases.
If you were sleeping this whole time, here are the bare minimum takeaways to keep in mind. First, memorize your strong acids and bases. Don't lose points on that, and always identify them in problems.
Remember, Henderson Hasselback is your friend, so when in doubt, Henderson Hasselback it out.
When you approach a problem, try to identify which of the 4 problem types it is: dissociation, equivalence point, half equivalence point, or unbalanced. If it's dissociation, go to ICE, but if it's any of these reaction types, then go to BCA table.
I believe all of you will do phenomenally on this test. Now here's one last problem we'll close off with. Why did the acid go to the gym?
Wait, what's a gym? I didn't read that in my textbook.
To become a buffer solution! Get it?
Bye.
Welcome, class, to a review of acids and bases. Today
I cannot read that.
Oh,
Okay,
here, I'll make it bigger. Can you read this?
Yep.
Okay.
For the basic stuff, like what an acid even is, refer back to Hudson's Unit 4 videos. If those don't make sense, you have my permission to whoop. Wait, what is that? Yeah. Okay.
Only one hydrogen proton. pH and POH are always related to each other through the water dissociation constant. Kw equals 1.0 times 10 to the negative 14, which also equals H3O plus concentration times OH minus concentration. Remember, pKw equals 14 from this exponential constant, which equals pH plus POH. Third, pH and POH are always related to each other. Wait. Third, pH and POH are always related to each other through the water dissociation constant. Okay. Third, pH and POH are always related to each other through the water dissociation constant. Kw equals 1.0 times 10 to
Change the Kw constant.
How am I supposed to get wet? I can't be laughing. Good try, but none of those are correct. Even H.
Off to the side. This draws the electron density, all the negative charge from these atoms. Isn't there another explanation? Like, you could also look at the resonance structures of a conjugate base. If the conjugate has a lot of
Yep, that's right. And don't worry about explaining this straightly. Yep, that's right. And don't worry about explaining the strength of strong bases because it's not on the test. They only have to accept. Man, my
cup of water and 20 milliliters of 0.5 mole. Molarity.
Molarity. Okay.
Dissociates completely.
Yes, and
Dissociates in water. There's only the conjugate left, and oh my god.
let's use voom voom to calculate.
Let's look. Oh my god. Let's look at a expression for the kV value. See, we can neglect the change to our initial value. Does that make sense?
So that covers dissociation for strong acids and weak base. Once again, sorry, Johnny. There's find POH concentration. Take. Okay, let's BCA. BCA is a. Okay.
You could say it however you want.
F minus. When you plug it into Henderson-Hasselbalch. Why did I say that?
Hasselbalch. Bulk.
Hasselbalch. You need to have an Alright, we all know what a titration is. You are sorry. Your indicator changes color. What am I saying? With a solution of this will be like
Here are some key components of the graph that you'll need to be able to increase or decrease in pH based on if that's one drop of your titrant. Wait, where? This equivalence point might not be exactly 7. Might not. Might be.
okay. Where is it going?
Okay.
And that just wraps up. And that just about reviews our. I believe all of you will do phenomenal. Oh, okay, that's kind of risky.